All right, so we're gonna start with the history of the periodic table, which you guys were just doing anyway. Um, and as scientists, a lot of times all we do is somebody comes up with this idea or this concept or notion, they test it, and then other scientists come behind them and say, yeah, I think this is right, but I'm gonna add on that you also can do this. So as we get more knowledgeable about things, we just go through and we revise stuff. Okay, so that's same thing with the atom, how they thought it used to look to what it looks like now, to what they think it looks like now. Same thing with the periodic table. So when we look at some of this older stuff, okay, they're talking about all these different scientists and how they developed the periodic table. Like the first scientist who was thinking about it being like made of like it's either earth and metals and all kinds of stuff. And as we went along, okay, we kind of developed, these scientists kind of came up with different notions. So the scientists that I want you to know, there's two, okay? The first one was the one that you watched the video on. He is known as the father of the periodic table. And you need to make a note that he is known as the father of the periodic table, okay? Father of the periodic table. So there's two. Mendeleev or Mendeleev, it just depends on how people pronounce it. All right, he's from the late 1800s, father of the periodic table. This is the guy who was like crazy smart, right? Like he had these ideas, okay, like in the video, for instance, what was the crazy part about the video in terms of like what he told that French scientist when that French scientist discovered an element? Yeah, exactly. He said, actually, you didn't discover that element. I discovered it. I just discovered it in my head. Like I knew that element existed. I just didn't know where it was. But the crazy thing, even crazier, was that he was right. Like he knew when he started building this periodic table that there were these elements that existed or should be in existence, but they just hadn't been discovered yet. Okay. Now, how did he arrange his elements? You have atomic number and you have atomic mass. So remember, when you have a periodic table box, like if it's oxygen, oxygen is number 8, and then down here it might be like 15.999. Okay, which one is the atomic mass? The one on the bottom number. Okay, and that's how he arranged his. He arranged his by atomic mass. Okay, now realistically, the periodic table should be arranged by atomic number, which tells me the number of what? Yes, number of protons, okay? Now, he did see the connection between atomic mass and then different properties, okay? But he is the first one who's credited with arranging it like periodically. In other words, it goes so far and then it like repeats, okay? He did predict, this is the crazy part that we were talking about earlier. He predicted the existence and properties of undiscovered elements. And when he did that, he left blanks because he knew there was like different elements that should go there. So Mendeleev is one guy that you absolutely have to know, okay? The other guy that I want you to know is Moseley. All right, so Mendeleev was in the late 1800s, Moseley early 1900s, okay? This is the periodic table. We use his periodic table today, okay? So this is our current periodic table. This is whose we use. And really, the big difference is that he arranged his by atomic number, okay? So the number, Ryan just said, atomic number tells us the number of protons, that's the atomic number. So that's how he arranged his, and that is correct, okay? So it goes in order of increasing atomic number. So atomic number, all right? And that is how we essentially have the true periodic pattern, okay? True periodic pattern. All right. Periodic law, that's your next blank, okay? That's your next blank. That's nothing but just saying it's increasing periodic repetition of chemical and physical properties of the element when they are arranged by increasing atomic number again, okay? So in other words, periodic law is just saying after you go through so many elements, okay, or so many columns, like 8, okay, then it repeats. Okay, there's a repetition. It's like, oh, all of these elements happen to, fall into this category. They all happen to have 6 valence electrons. After so far, they all have 6 valence electrons, or they all have so many rings, or they all have, this property or that property. All right, everybody got this down because I'm about to clear it off. Let me see, okay, Ryan, is this in the way? Okay. Yes, do you need it now? All right. Okay. All right. All right. The last one is atomic number. Okay. All right. So now we're going to get into the organization of the periodic table. If you have your paper copy of the periodic table, it would be good because I'm going to ask you to draw something on it. If not, it's okay. Okay. All right. So let me clear this off. All right. All right. So now let's talk about the organization of the periodic table. We should, let me go down a little bit. All right. We should already be familiar with our element box. You should be very familiar with that now. You should know which one is atomic number, which one is atomic mass. You should know the element name and the symbol. So let's talk about states of matter really quickly because I didn't mention that. All right. So this is not in your notes, but you need to make just somewhere on the side, you can do states of matter. All right. And we already talked about this, states of matter. All right. There were 3 states of matter. What did we say most of the elements were? We said most of them were solids. And if you remember, when we look at our periodic table, the solids were the black ones. Okay, so I just want you to make a note of what each state of matter, what color it is. Because if I give you this periodic table and I say, what state of matter is aluminum? You should be able to look at aluminum, look at what color the letters are, and tell me that it is a what? Solid, liquid, or gas? Aluminum. It's a solid because the letters are black. Okay, so if you see aluminum right here, the color of the letters is black. Okay. All right. So let me go back here. All right. So states of matter, let's just say I'm going to color code mine, but you can write it on yours. But, blacks were solid. Okay. Solid. And then what color were gases? Yes. Gases were red. And then liquids? Blue. And then there are some white or clear ones, okay? So make sure you know your states of matter, solid, liquid, gas. These are color coded. Okay, so this is blue, red, and black. All right, they're color coded. There are some white ones. We tend to say we don't worry about those, but what we're saying is those are kind of like, they're actually kind of synthetic, man-made. So, as scientists, people like to say like, oh, well, I created this, that, and other. And that's why when you get down to these lower numbers, there's really some weird name ones. Okay, so like 106 SG, that's Seaborgium, is named after a guy whose last name is like Seaborg or something like that. There's one called Americanum. There's one called Einsteinium. So they're named after people or countries, okay? All right, let's go back to our notes. Groups. Groups are also known as families or columns, okay? They're also known as families or columns. Groups or families. All right, those are columns. Left to right or up and down? What do you think? A column. Yes, columns are up and down. All right. There are 18 groups on the periodic table. All right, 18 13 groups on the periodic table. All right, periods are rows. All right, and those go left to right. And how I remember it is, if you read a sentence, there's a sentence, blah, 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 and then at the end is a period, okay? So you read a sentence left to right, right? That's a period. There are 7 periods, okay? 7 periods. Representative elements, okay? Representative elements are groups 1, 2, and then 13 through 18. And I'm gonna write all this and then I'll go back and explain it, okay? And then we also have the transition elements, okay? Usually we call them the transition metals, okay? And this is just D block. So 4 and 5 together make the entire periodic table, okay? 4 and 5 together make the entire periodic table, but 4 is just the periodic table minus D block, okay? All right, so let me show you now what I just to make sure we go over families and columns. All right, everybody got this down because I'm going to, it's going to be on top of my periodic table. I'll give you a second, okay? So groups are families or columns. So those are the ones that go up and down. Now, there are, remember like the first column, okay? That's going to have a family name. That's one of the ones that you should have wrote down from your notes. We'll talk about that in just a second. And those are columns, all right? So anybody on, I'm going to go ahead and clear, make sure nobody online is writing. All right. Let me see if I can just switch over. It might be too much writing though. All right. I'll wait before I erase. All right. So basically, a column looks like this. Like this is a column. Okay. So this is a column. So when we say the representative elements, we're including here's group or family 1, group 2, and then group 13 through 18. These are what we were talking about when we said the representative elements, okay? D block or the transition block, okay, transition elements are right here. So this is D block. It's just like when we did our electron configuration. So we had S block, P block, D block, and F block. This is D block, okay? The reason why we kind of pull D block out from everything, remember how like when we did electron configuration, their rings drop down, okay? They're different because let's talk about why these columns are called families, okay? Tell me one thing that everything in this group would have in common. Can somebody tell me one thing that every single one of those elements would have in common? They are all in the same column. That's true. Anybody else remember what would be the same for every one of them? What if I drew something for them and it would look the same for all of them? Amount, not rings. You're close though.
Valence electrons?
Yes, exactly. Valence electrons. That's what's going to be the same for all of them, okay? So all of these are going to have, for instance, 6 valence electrons. All right. Valence electrons are like our genes. Like if, you know, if it's me and my parents and my siblings, we all have the same genes. We're all in the same family. That's why these are called families as well. Everybody in this group has 1 valence electron. They have the same genes. Because they all have 1 valence electron, that's what makes their properties similar. That's what makes them, it's like their genes, okay? Same thing here. Everybody here has 2 valence electrons. 3, 4, 5, 6, 7, and 8 valence electrons. The reason why we leave out D block is because what does transition mean anyway?
It moves your valence.
Right. It can move or it can change. Transition means like trans means change, right? So because of that, all of these elements down here in this D block, okay, down in D block, they change sometimes. Sometimes they have two valence electrons, sometimes they have three, sometimes it's weird. They get different charges, okay? So because of that, we just kind of group them all together. That's like a family. We just say, all right, D block is a family. Everybody else has a particular number of valence electrons, all right? So that is your groups or your families, all right? That's your groups or your families. Let me clear all of this, okay? Your periods, there are only 7 periods, okay? If you look here, period 1, 2, 3, 4, 5, 6, 7. And a period goes this way, okay? So they go left to right. So periods are easy. Guess what periods tell you? Think about when we did board diagrams. What did it tell us? If I was doing a board diagram for,
Rings.
if I was doing a board diagram for this, why is it significant that it's on the 3rd period?
It has 3 rings.
Say again. You're right, but I couldn't hear you. Say it again.
It has 3 rings.
Yes, exactly. It tells me the number of rings, okay? So periods or rows, make a note on your notes, okay? Because I didn't write that. Periods or rows tell you the number of rings, okay? Periods or rows tell you the number of rings. That's what the period tells you. Period is equal to number of rings. So we already knew that, but again, we're seeing how the periodic table tells us a lot of stuff. So now we know it can tell us the number of valence electrons. We can know the number of rings. We know that everybody in the same family has similar properties. Okay, so that's what we got so far. So let me erase. All right. Let me see. Yeah, a little bit more notes and then we'll be done for the day. All right, so we talked about groups, families, rows, periods, representative elements, transition elements. Now, and we talked about states of matter, okay? And we talked about states of matter. Now, if you have your periodic table, if you have it, if you don't, it's okay. We're going to talk about metals, non-metals, and metalloids, which is just really kind of a combination of a metal and a non-metal, okay? Tell me something you know about metals in general. Anything you know about metals. Some properties. If you look at something, how do you know it's metal? A lot of times it has luster. What does luster mean? Anybody know? Yeah, a lot of times metals are shiny. Okay. What else? We learned some properties a long time ago. What about wires and stuff? Yes, they can conduct electricity very well. Would you pick up a hot pan off of your stove? No, because they conduct heat very well as well. All right, so here's how we're going to tell the difference between metals and non-metals on the periodic table. It's pretty easy. Well, I say that. All right, so here it is. If you start right at the beginning of P block right here, okay, we're going to draw a zigzag line or a staircase, okay? So the zigzag line starts here, and then you just go over and go down, go over and go down, go over and go down, go over and go down like this. All right. That's our zigzag line, okay? And I will draw it on this one so it'll stay on there, okay? Anything to the left of that staircase or the zigzag line is a metal. Every single thing except for hydrogen, okay? Everything to the left of this staircase is a metal except for hydrogen. So let me go to my notes just for a second. I'm not going to erase my line, okay? But now we are right here. So metals. Metals are located to the left of the zigzag staircase line. Everything is a metal except for, again, hydrogen, okay? All right. Ryan already said that they have luster, which means they are shiny. We said they were good conductors of two things. What did we say? What was one? Yep, electricity was one, and then we talked about the hot pan. So heat, electricity and heat. It doesn't matter which order you write it in. Okay. We had these two really old vocab words. One meant it could be hammered into sheets. One meant it could be drawn into R. One started with a D. One started with an M. Am I? Not those are good D. Those are old ones. Not quite. One was, this one is malleable. I think we already talked about these. Did we use these words before? And ductile. Okay. So ductile is the one that can be drawn into a wire. Malleable is the one that can be hammered into a sheet. All right. I'm going to go back for a second. This question A is asking, what state of matter do you think most of them are at room temperature? Okay. You tell me, what state of matter do you think most of them are at room temperature? They are solid. That is correct. There is one that is not a solid at room temperature. See if you can find it. So there's one that is not black that is left of the zigzag line. You guys see it?
Bromine?
Left of the zigzag line. That is one, but it needs to be left of the zigzag. Hydrogen doesn't count only because it's not a metal. So it's a metal and it's not hydrogen and it's not a solid. You guys are getting warmer though. Nope, that one's black. Lithium's black. What is it? Yeah, don't count that one because you're right. You're technically right. Not 43. So one more. So not any of the white ones. I'll give you a hint. I'll tell you. Well, okay, I'll give you a hint. It's blue. So find the blue one.
80.
Yes.
Oh, mercury.
Yes, mercury, Hg. And if you think about it, mercury is a liquid at room temperature. Guess where you usually find mercury? Anybody know where you usually find it? I'll tell you. You usually find it in a thermometer. Okay, so this is mercury. And it is a liquid. You don't have to write all that. I'm just telling you that it's a liquid. So most of them are solids at room temperature. They're shiny, they're malleable, they're ductile, they're conductors of heat and electricity. That is metals. We're almost done. Oh, yes, people were. Sorry, I missed some people in the chat, but yes, you were right. Thank you. All right. So now we got our properties for metals, okay? And I want you to know these because I may ask something like, give me an element that is, I may say, the reason why this is important, so I may say, give me an element that's a metal that has this many rings and this many valence electrons. Those are the type of questions I can ask you, okay? All right, so now let's talk about non-metals. If metals are to the left of the zigzag, non-metals are to the right of the zigzag line. So that of the zigzag or staircase line. So that includes everything to the right, including the one that we left out the first time, including hydrogen, okay? All right, so let's see. Let's go look at what they look like now, okay? All right, when you have non-metals, we're looking to the right of the zigzag line. So we're looking at everything to the right. What do you think most of those are? Yes, they're mostly gases, okay? So they're mostly gases, but you really got a little bit of everything. You got some solids and you have a liquid as well. So let's go back to the notes. All right. So most of those are gases at room temperature. Let me Let me move this up so you guys can see. All right, it's gonna be kind of weird because I don't want to get rid of my zigzag just yet. Oh, there we go. Okay. Sorry, I'm trying not to get rid of my zigzag line so we can still have it. All right, so most of them are gases, okay, at room temperature. A lot of them are brittle, which means they easily break apart. They are dull, which is just the opposite of shiny, and they are poor conductors, okay? Poor conductors. All right, so this is located to the right. This is non-metals. Located to the right of the zigzag line, including hydrogen, gases mostly, but you have all states, okay? All right, and then the last thing that we're gonna talk about, okay, are metalloids, all right, metalloids. Metalloids touch the zigzag line. Now, let me tell you what I mean by touch. They have to have a full side on the zigzag line. They have properties of both metals and non-metals, and they are used in computer chips, all right? There's a lot of this non-metalloids in the back of our cell phones, okay? All right, there is one exception. I'm gonna see if you guys can figure it out, okay? So let's look at what our non-metals are. And it might be helpful for you to just write down all of them, okay? Or at least the symbols. All right, so let's go back and look at our metalloids. All right, here we go. Metalloid, so we said metals to the left of the zigzag, okay? Non-metals to the right. Metalloids have a full side on the zigzag. So that means, for example, let me use my mouse here, okay? For example, boron has a full side on the zigzag, like he has a full side on the carbon is just touching a corner. Carbon would not be a metalloid, okay? Carbon just is touching a corner. Boron has a full side, it is a metalloid, okay? Aluminum is the exception, okay? He's touching the line, but he is a full-blown metal, okay? So he's the only exception. Silicon has a full side on it, so he's a metalloid, okay? Germanium and arsenic, both are touching, they are metalloids. Gallium has a corner, he is not a metalloid, he's a full-on metal. Phosphorus has a corner, he is not a metalloid, okay? So let's go back. Boron, yes. Aluminum, no, he's the exception, okay? Silicon, yes. So Si. Ge and As, germanium and arsenic, yes, metalloid, okay? Sb and Te, full side, yes, they are metalloids. That's antimony and tellurium, okay? Polonium and astatine, yes, full on metalloids. They have a full side touching, okay? And then we don't really go down this far, so you don't have to worry about these. But POAT, SBTE, GEAS, and then Si and B are your metalloids, okay? Those are your metalloids. All right. All right, let me go back to the notes. Let's make sure we got everything I wanted to get. All right. The exception here again is aluminum, Al. He is a full-on metal. Okay. All right. On Thursday, we're going to do a little bit more on organization. You need to, oh, let's do this really fast before we go. Let's do family names are the ones you know. You should have known 4 family names. I'll tell you the ones I really, really, really want you to know, and then that'll be it for the day. All right. I need a family name for this family, this family, this family, and this family. I'll take anybody for either one of these. Very nice. Ryan said this one is the noble gases. Very nice. They are super unreactive because guess what? When I draw a Bohr diagram for them, their last ring is completely full. They are happy. So they are noble gases. They do not want to react. Very nice. Very nice. Janae says alkali metals is for column 1, alkali metals. Oops. Excellent. Anybody else? This one starts with an H. Anybody remember this one? And it's not hallucinogens. That's what somebody told me yesterday. Does start with an H though. Halogens. Very nice. Halogens. And then I'll give you this one. This one is alkaline. So it looks like that first one, but alkaline earth metals. Make sure you know those family names. All right, make sure you finish your, I'm gonna put in those grades for the F puzzles in like 5 minutes. All right, see you guys on Thursday.